let's continue on this journey of how to find limits of more complicated functions. Next up is piecewise functions. If you understand how to take limits of piecewise functions, you probably are doing pretty good on most functions in this class. So my favorite example, absolute value. The limit as x goes to 0 of the absolute value of x. The question is, do you know how to define the absolute value of x? Take a second. How would you define it? If you were like most people, you in your head drew a picture of what it looks like. So off to the right here, it looks like that old friendly kind of V shape like this. Okay. If you were like some other people, you maybe said, hey, it just makes things positive. Whatever is on the inside, it makes positive. But neither of those are really examples of what we might call a mathematical definition. So the standard definition of the absolute value of x looks a little bit like this. It does one of two things. And those two things are broken up by if x is negative or x is positive. So it's a piecewise function. So let's do this bottom one first. If x is positive, what does the absolute value do? Nothing. It does absolutely nothing. So how do I write that? It takes x and it leaves it as x. Great. Okay, well, what if it's negative? Well, it's going to make it positive. How could I take a negative number and make it positive? And I don't get to use the absolute value. Well, if it's already negative, and I negative it again, then it should be positive. So this is my piecewise function. If it's negative, take its negative, that'll make it positive. If it's positive or 0, do nothing. So I've got this beautiful piecewise function. Normally what I'm going to do if I take a limit is I'm going to say, okay, am I in the top domain? Am I in the bottom domain or some other domain? Or am I on a breakpoint? And in this case, the limit is going to 0. And so I am right on that edge of these two, of the top and bottom. So I need to do something that we've brought up before, which is consider the left and the right limits. So when you have a piecewise function and you are in between two of the domains, the subdomains, then we are just going to say split it up into a limit from the left and a limit from the right. So as I come in from the left of absolute value of x, that means my x's are always negative because they're less than 0. If they are less than 0, well, my absolute value of x can be rewritten as just negative x. If I come in from the right, then all the x's I'm looking at are positive. I'm coming in from the right side here, which means that my absolute value of x can be rewritten as the definition on this domain, which means this is just an x. Easy peasy. Now we're going to use that fun theorem we had, which says that this limit exists if and only if the left and the right limit agree. So we just got to find these two limits. Okay, what happens to negative x as x gets closer and closer to 0? Well, this is just going to go to negative 0. Well, it's just going to go to 0 because negative 0 is 0. What happens to x as x gets closer and closer to 0 from the right, always staying positive? Well, it's still just going to go to 0. Great. So the left and the right agree. So the limit exists. It doesn't just exist, we know what it is. It is whatever they agree to. So this limit is a 0. Cool. And that's how we deal with piecewise functions when we are at the split point between two of those subdomains. Okay. And I hope that if you look at this picture too, you see, even though there's that sharp corner, and even though my drawing is a little wiggly, that it's really clear what that value is at 0, right? That it agrees nearby, that it's going to 0, right there. Okay, let's see if we can make this a little, I don't know if it's harder or not, but it's similar and different at the same time. That's all we're really going for. Absolute value of x over x. Maybe take a second, see how far you can get. It's going to be a similar approach. You could even try to graph it. Okay, I'm not going to wait for you though. I hope you pause the video when you get those chances. Again, if I tried to plug in, if I tried to plug in here, I get a 0 over a 0. That should be telling you we got to do some work, right? So let's do that work. I don't like this absolute value. I don't like that piecewise defined function right at that break in its subdomain. So I'm going to, again, take a limit as x goes to 0 from the left and a limit as x goes to 0 from the right. Why going to 0? Well, that's where this big limit's going to, right? That's what we are trying to figure out. So again, from the left, what's happening to my absolute value if x stays negative? Well, in that case, absolute value is just negative x, as long as x is less than 0. And this x is just going to stay right where it is. Okay, if x is going to 0 from the right, that means x is staying positive, which means my absolute value of a positive number is just x over x. Cool. Okay, these are still in that 0 over 0 form, but it is much more clear how we would simplify this. I hope you agree. So this is going to equal, if those were to cancel out, here I'll even do this in 2 steps. The limit as x goes to 0 from the left of negative 1. Notice this is not defined at 0, but the limit looks everywhere except for at 0. And so I am allowed to cancel those out in the limit. Okay, you can cancel at will in the limit and not worry about the idea that maybe the top and the bottom are both zeros. It's one of the reasons why we love limits. Okay, this limit is just going to equal, it's a constant. Our limit laws tell us what to do with a constant. They stay a constant. They don't really care what x does. So boom, negative 1. On the right here, I'm going to do this much faster. The x's are going to cancel to get a 1, and that constant is also going to just stay a 1. Great. So my limit from the left is a negative 1. My limit from the right is a positive 1, and I think that should hopefully tell you that, well, they don't agree. Don't agree. So the limit does not exist. And up here, we're just going to go ahead and write dne. Boom. Does not exist, which is different from undefined. Okay, so that limit does not converge. Let's go ahead and graph this real quick if we tried. This function, absolute value of x over x. I'm going to, it looks like as long as x is bigger than 0, then the top is going to be positive, and we just get x over x. So it's just going to be a 1. And as long as it is less than 0, then, well, the top is going to be positive, and the bottom is going to be negative, and we get negative 1. Okay, I'll give you a little scale here. This is a 1. This is a negative 1. All right, so I hope you can see from that that limit shouldn't exist, because coming from the right and the left, we get very different things. In particular, that's going to be called a jump. When the left and the right limit are both finite and don't agree, it's a jump, right? We have to jump up to get to that other line. Great. So that's basically how piecewise defined functions work. And they are good practice, and they usually, at least one shows up on tests to make sure that you are understanding really in detail what's going on with some of these more complicated limits. All right, let's change topics ever so quickly into a famous theorem. It's called the Squeeze Theorem. This theorem, if I was going to guess, often shows up on homework, usually not on tests that I write. This is very instructional, but not the most useful thing in Calc 1. So I want to talk through this, and I want to explain why it's worth talking about right now, but I also want to help you feel better knowing it's probably not going to show up on any tests, maybe on homework. So the Squeeze Theorem says this fun thing. It says if I have 3 functions, f, g, and h, and we know that f is smaller than g is smaller than h near some point a, and we know that the limit as x goes to a of f is the same as the limit as x goes to a of h, which is L. Okay, so I've got a lower bound f and an upper bound h, and they are equal. Well, then g is squeezed in the middle, so that limit has to exist. And that's what this last line says. Then the limit as x goes to a, g of x equals L. So if I can bound it below and I bound it above and both those bounds agree, then I actually know the whole thing. Okay, I'm going to give you an example in just a second, but why is this important? One, it's a named theorem, it must be important, and it's important for you to practice reading math and theorems to get better at it. Two, as you move on with more complicated limits and just more complicated things in math, this idea of bounding becomes really important. So think of this as a light introduction to, in the big world of analysis, often what you have to do is compare complicated functions to simpler functions to try to bound them from above or bound them from below to try to get some idea of what's happening. So let's do an example, and I think I can make this a lot more clear. We saw before this terrible function. It's also an amazing function, sine of 1 over x, that makes that topologist sine curve that goes up and down infinitely many times. And this thing doesn't have a limit at 0. However, if I put, say, an x squared here, it does. So let's think about this for a second. Sine of x has an upper and a lower bound. So we want to find a lower bound f of x. We have the original function, g of x equals x squared sine of 1 over x. And we want an upper bound also, h of x. So we think to ourselves, okay, I think this thing is going to 0. Maybe by graphing it. What could we find here that would be an upper bound for sine of x? Well, it's naturally bounded. And I hope you think to yourself, I know what the upper bound for sine of 1 over x is, because it's 1. Sine of x is never bigger than 1. So x squared sine of 1 over x also can never be bigger than x squared, right? Because x squared is also never negative. As a lower bound, we could say, how small does sine of 1 over x get? And I hope you know how small sine of 1 over x gets. And I really hope you didn't just say 0 to yourself. The smallest sine of 1 over x, the smallest of any sine of anything, is -1. It goes up and down between -1 and 1. So the lower bound here is -1. Okay, so this g is always going to be in between negative x squared and positive x squared. And if I was going to graph this thing by hand, that's exactly what I would do as well. I would say to myself, okay, let's go ahead and quickly graph a parabola. I'm just going to sketch this out here, not a perfect parabola. Okay. And let's go ahead and try to sketch out the negative of that as well. Okay. And then what sine of 1 over x is going to do is go up and down in between those two. And it's going to start off real slow like. Something like this. And then it's going to start going up and down faster and faster and faster, infinitely many times, but always staying in between those two curves. And similarly, it's going to, on the other side, it's going to look like just the total opposite of that. It's an odd function. Okay, so infinitely many up and downs close to 0, but still wedged in between this upper green parabola and this lower green parabola. And this is my x squared, and this is my negative x squared. Okay, and all this theorem is saying is that, yeah, as long as you can kind of wedge your function in between two simpler functions, then you know what's happening. And so we do. The limit of negative x squared as x goes to 0 is 0. The limit of positive x squared is also going to be 0. They're touching right there. And that tells us that this function right here also has a limit, which is 0. It's not defined there, but it still has a limit. So this is a hole right here because the left and the right limit agree, even though it's not in the domain. Great. That is the squeeze theorem. It is super neat. It is totally worth, at this point in your career, thinking about, hey, I have a complicated function. Can I approximate it or bound it by a simpler function? This is what's going on in my head all the time while I'm teaching too. When someone asks me a question is, do I kind of know what's happening because I understand some simpler function that's going to bound this above or below? And the squeeze theorem is the nicest case, where you have an upper and a lower bound. Great. So named theorem, good for you to think about. Probably not on a test, so don't worry too much about that. All right. It's been fun. A lot of this limit stuff, you just got to practice until it becomes intuitive and second nature. So go practice, practice, practice. I believe in you.